Hello and welcome to a brand new video. In this video we're going to be taking a look at emulation. How does emulation work? And how can you get started in programming an emulator? In this tutorial we're going to be describing and creating a CHIP-8 emulator, which is famous for games such as Pong, Space Invaders, Brick Breaker, among a lot of others. This tutorial will be based in the Zig programming language. However, the instructions should be generalized enough that you can do it in any programming language with very little modification. So without further ado, let's go ahead and get started. So what exactly is an emulator? An emulator is basically software that allows one computer to behave like another in order to run applications. So this means something like if I have a Game Boy game and I want to play it on my PC, I would need a Game Boy emulator for that PC. There are two different levels of emulation, which is going to be low-level and high-level emulators. Low-level emulators are focused on emulating the hardware of whatever system it is, whereas high-level emulators are more so focused on implementing the software and OS calls. This can be very useful for more modern systems, being able to run in emulators way faster. So what exactly is CHIP-8? CHIP-8 is not technically hardware, it's more like a virtual machine. However, it does pretty much implement all of the ideas of what hardware is. It was quite literally a virtual machine. And if we take a look at some of the links that I have included in the description, this one is the technical reference. And if we go ahead and go to the specifications, we can see the basic design and what the CHIP-8 is. All you gotta know is that CHIP-8 has 4096 bytes of RAM, so 0000 to 0xFFF. This is hexadecimal notation, and it will be used within the context of this video. The first 512 bytes are where the original interpreter was located, and should never be used by a program. Almost all of the CHIP-8 programs start at 0x200, which is 512 bytes in, and this is where we're going to set our program counter. You'll also have basically a special purpose register for the delay and sound timers. And it's important to note that you have VF, which is the final or the 16th register. And this one's usually used as a flag. So if you're ever writing a CHIP-8 program, try not to use the VF register. There's also pseudo registers, which aren't necessarily actual registers, but they are things that are required for the program to run. The first one is the program counter, which is a 16-bit memory address, and that stores a currently executing function, and the stack pointer, which will be pointing to the last place where a function was called from. Other important considerations for the CHIP-8 is that it has a keyboard, which is a 16-key keypad with the following layout: 123C, 456D, 789E, A0BF. And these are obviously hexadecimal as well. Then we also have the display. It's a 64 by 32 monochrome display in any color. And then whether or not the virtual machine's graphics representation is set or not determines whether that pixel is on or off. The CHIP-8 draws graphics using sprites, which are up to 15 bytes. Each single byte that you read across is going to use every single bit in that to represent whether a pixel is on or off. The delay timer, basically, you just subtract 1 from the value of the delay timer at the rate of 60 Hz, and when delta timer is 0, deactivates. Sound timer is active whenever the sound timer register is not 0, and it also decrements at the same rate. However, it will always play the buzzer sound while it's greater than 0. So then you come across the instructions. There's 36 total instructions. That sounds like a lot, but they're all pretty easy to do. And then basically we have these different formats here. So basically you can sort by whatever the first nibble here is. A nibble is just one single hexadecimal. A nibble is basically one hexadecimal digit, so the first nibble here determines what instruction it is, and then there are special cases that you'll have to search for, and then you'll have these notations. This is 2, and then it's NNN, where NNN is basically an address. So you could figure out where that address is, and this is how you jump to or call a subroutine at that address. You'll also have XKK, this is a similar one, where basically X, in this case, is going to be what the register number is, and then KK is a byte, and that's similar. And then you'll also have this format here where it's XY, and then sometimes it's another number, XYN or XYM, where X and Y are now the registers, so VX, VY, and then the last one is a mode. So that matters for the ALU instructions, which are the 8 series here, where it's XY0, 1, 2, 3, 4, 5, and all these other instructions. For this, if you guys want to read an article, I recommend this one from multigesture.net. It's pretty cool. It goes through pretty much all of the basics. It doesn't necessarily show you the implementation. It's more so just the general concept of how this thing works, and it's a pretty good source. And then if you want to see the implementation of this, you can go to this James Griffin's CHIP-8 emulator, which is basically the literal interpretation of this tutorial. The other two things that I have here are a test ROM. This is a CHIP-8 test ROM, and it just it goes through a bunch of instructions and figures them out. And there's also this one from C8int, and basically it's another test. But if you look at the source, it will basically print out a number based upon which test is executed and which one fails. So if one of these fails, it will give you a code, and then you just refer to this key. So starting here, I've downloaded SDL2. I'm going to be using SDL functions. I won't be instructing you specifically on how SDL works, but we're going to make some basic glue code, which you can skip over if you're not using SDL, for basically creating a window and displaying stuff to that window. So I'm going to initialize my project here. This is a sig init exe, which creates our build files here. And then I'll go ahead and link in SDL2. Alright, that's set up. Let's go ahead and initialize SDL. I'm going to try to make this as quick as possible. So we're going to start with main, and we're going to create a function init and dinit. And we're just going to call init and then defer deinitialization. Also, I'm going to create an allocator. You need to do this in Zig if you ever want to allocate memory, so it's pretty much required. Alright, we created a blank allocator here. Let's go ahead and initialize SDL. So, to start off, let's get SDL imported here. Zig has this awesome feature called C-import and C-include, where you can just go ahead and include a header file like sdl.h, and suddenly you have access to everything inside of SDL. So if I wanted to do SDL init, it would automatically be populated here, which is amazing. So we do need to check if SDL init fails, and if it does, we need to exit the application. So to do this, we'll do a panic. This is similar to throwing a runtime error, basically, if you've used C++ or whatever language you're using, if it has exceptions or error handling like that. Basically, just create variables for the window, a renderer, and a texture. This is all you will actually need. Creating window is pretty simple. Windows equal to SDL, SDL create window. And then we'll call it CHIP-8. Then we're going to center it on the X and the Y, so it shows up in the middle of your screen. And then you can choose any resolution here as long as it follows the aspect ratio 64 by 32. So I'm going to do 1024 by 512. Depending on your display size, you might want to make it smaller. And then we're going to create a renderer here with the default settings. Finally, we just need to create a texture. This will actually be what represents our data, or basically our screen in general. So we create a texture, and it's renderer. I'm going to be using a texture here, a texture format. So it's going to be STL pixel format, and I'm going to use RGBA CHIP-8, which is just going to be 1 byte for R, G, B, and A. And then this is the most important. It needs to be texture access set to streaming, so it can be updated essentially. In deinitialization, it's pretty simple. You just destroy the window and call STL quit. We're going to need to create a main loop here, so we're going to create a variable called keep open. And by default, that's true. And while we're keeping it open, we're going to call an emulator cycle, which we'll deal with in a second. And we need to pull for events in STL, so STL event. And based on what type of event we get determines what we're going to do. I'm going to create an else here, just for safekeeping, in case anything else gets thrown that we don't care about. So when quit gets called, keep open becomes false, and we exit. So here, a couple of rendering functions. Called render clear, then render a copy of the texture to the screen, and then you call present. And then here, we're just going to sleep, and you'll sleep for 16 milliseconds. Or, yes, 16 milliseconds. And this way, you'll have that 60 hertz going for you. Another to-do to put here is that after the render clear, before the render copy, we need to do we need to build the texture. So we have to refresh the texture based upon what's currently displaying on the graphics. You can technically make this faster by having a flag that you set in the emulator, whether or not you need to rebuild a texture, but this is fine. I'm going to create another file here called CHIP-8. In Zig, you can use files as structures, which is pretty cool. So I can do const CHIP-8 equals import chip8.zig. And now that is actually a structure that I can create. I'm going to allocate a structure here. So this will be a variable. And we'll just call it, we can call it CPU. And then it's just going to be a pointer to CHIP-8, which is currently undefined. And then to get that, we'll do CPU equals allocator.create CHIP-8. And it has to be a try, because otherwise it returns an error. So let's get into the CHIP-8 itself. We're going to create a function here called init. We also need this to, if we want this to be a member method, we have to create this thing called self, and it's just going to be whatever this current structure is. And we need to take in a self pointer to itself. And then we can go over here and call CPU.init. And it will work the way you think it will. Another to-do thing we have to do is load a ROM. In this case, we'll just be doing command arguments, but we'll come back to that in a minute. So if you've gone ahead and skipped ahead, I've created the basics for initializing our STL context here, and I've added a little bit more utility to this. So we're going to create a structure or a class, whatever it is in your language of choice, that's going to be your main system or CHIP-8 or whatever you want to call it. It's going to be your system that you're trying to emulate. and currently doesn't really have that much content of what it does. But it will have an initialization. It has to have an emulator cycle, and then you have to build a texture or find some way of getting your graphics array to be displayed on the screen. And we'll also need to load a ROM. These are the fundamental things that you need to do. So you need to initialize whatever your window context and everything is. You need to then go ahead and create a version instance of your system and initialize it. You need to load a ROM. Sometimes you need to load the ROM before you initialize it, sometimes after. It doesn't really matter that much. And then we have a continuous loop that does emulator cycles and then presents to the screen and uses whatever texture or graphics method that you're using. So for now, let's get on to the technical details of the system. I'm going to import the standard library and a couple things from C. So the C stdlib is C import, C include, and it's stdlib. And I can do the same thing with time and do time.h. And this will be done for the random number generator. So there's a few things that you need to know for your CPU. Your CPU should probably know what opcode that you're executing, which is operation code. And if I set that, it's going to be U16, because if we look at the spec, the opcode is going to be a U16, because if we look at the spec, there is clearly 16 bits here, or 4 nibbles, or 2 bytes, however you want to say that. Every instruction is like this, so you have to have opcode being a U16. The next thing you want to have is you want your program memory. Sometimes you can create this as a separate class or separate buffer, depending on if there's memory access rules and stuff like that. But in this case, we just literally can allocate 4096 bytes on the stack. Sometimes your compiler will complain about this because it is a large stack allocation. The other thing you will need is graphics. As you can see, graphics are 64 by... The graphics, as we discussed, are 64 by 32. So you can go ahead and do that as another 2048 bytes as well. Then we need some registers. We have 16 general purpose registers, so that will be that. And then we have special registers now. We have the index register, which is a single U16. We have the program counter, which is also a U16. And then we'll have the timers. So we'll have delay timer, which is a U8, and we'll have a sound timer, which is another U8. We'll also need to keep track of what is going on with the stack. So we'll have the stack. We can do 16, and it has to be addresses, so it's U16s. And then the stack pointer, which is the current thing on the stack. We can technically do U4 here because there's only 16 things that we can point to, but it's fine. The last thing we should probably keep track of is what keys are being pressed, and we'll do that as an array of 16 as well. Alright, let's get into our initialization. Right now, I'm going to always go ahead and seed the random number generator, and this will have to be a U32. And then we're going to take a time.time at 0. And that will seed the random number generator. This is actually just equivalent to srand time null. Probably seen that before. And then we can do self. We're going to set the program counter to be the start, which is the start of our memory, which is 0x200 as we discussed. And the current opcode is going to be just 0. We can do the index is also going to be initialized to 0. And the stack pointer is going to also be 0. The delay timer is going to be 0, and the sound timer is going to be 0. Anything else I'm missing? I think that should be everything. And then we're going to go through the arrays now. So we're just going to do a for loop over each of these arrays and say that each one is 0. So we can do that for graphics, we can do that for memory, we can do that for the stack, the registers, and the keys. Stack, registers, and keys. Now, I don't think I'm missing anything else. The next thing we got to do is we got to import the font set. So to import the fonts are actually laid out and described here, but you can get it as an array. And if you look at the article here, this is the font set. I basically copied that over, and I'm going to copy this over now. So we can just declare this as a const. And then where do you load that? That's the big question, right? So we're going to do a for loop on the font set. Oops. And then we're going to have the character and the index. And you basically are just going to load it from 0, which is going to be your program, which is going to be your interpreter's memory space. So it will never be overridden by a program, because programs will be loaded at this 0x200 value. I'm going to create a convenience function here, and it's called increment program counter, which is PC. And then will just be a method of self, and just increments the program counter by 2. Why do we increment the program counter by 2? The reason is because every instruction is 2 bytes, whereas we have the ability to access 1 byte at a time through our memory. So, because we're not getting words of U16s, we're getting words of U8, we're going to actually have to go up 2, because each is 2 words. So the next thing, this is the entire meat of the emulator right here, is going to be the cycle method, which we can go back, by the way, and set up. So this will be running here. So CPU cycle. Last remaining things will be building textures, loading ROMs, and I might as well make a note here. Key presses need to be handled as well. So whenever you call a cycle, number 1, let's go ahead and get the opcode. So self opcode is equal to, I'm going to take the self.memory at the program counter, shift it right to the 8, and then OR it against self.memory with self.program counter plus 1. Then let's go ahead and grab what is the first nibble. So that is the very first, or most significant rather, byte. So we'll just call it first. And what you gotta do is just take the opcode and bit shift it right by 12. Why 12? Because it gets you over 3 nibbles. So it will be this. So where X will be what first is. And then we can do a switch case, or match, depending on what language you're using. And then if it's 0x0, if, so you need to detect which version of this it is. So if the opcode here is going to be equal to the 2 cases we have back here. So let's go in. So 00E0, that's clear screen. So if it's 0x00E0, this one is clear the screen, so we're just going to do a for loop on graphics, self.graphics, whoops. And then like that. And then the next one is a little bit more involved. This is the return. This is 0x00EE, I believe. Yes, return. It returns from a subroutine. This one involves the stack. So let's skip this for now, and I'll come back with the other stack instruction. Otherwise, this is actually considered a system instruction, which is a special instruction. This may be used, but it should be ignored by our interpreter, so we actually don't have to have an else here. And then we have to increment the program counter, of course. So we'll come back to that. 0x1. So in the case of it being a 0x1 instruction, this means that we need to get what NNN is here, which will be the address, and then the interpreter will set the program counter equal to NNN. This one is pretty easy. We're going to take the program counter, and literally all we're going to do is self.program counter equals self.opcode, and then you're going to AND it against the 3 bits over there, and that'll get you the address. That's how you get 0xNNN from it, and then it's a comma. The next one is a little bit more complicated, and here's where we're going to discuss the stack now. This is going to be the call instruction. So the interpreter will increment the stack pointer, put the current PC on the top, and then the program counter is then set to NNN. In our order, we're going to do it self.stack at self.sp is equal to self.program counter. So we're storing the program counter to stack. Then we're incrementing the program counter, or the stack pointer. And then we're setting the program counter equal to the self.opcode and 0x0fff. And there you go. Now you have that. So the opposite has to happen here when we return from it. So what we do is self.sp minus equals 1, and self.program counter equals self.stack at self.sp. So 0x3, this is a skip execution, or skip next instruction. And basically so it's 3xkk, so we need to get the x, so that will be our register, and then kk will be a byte. So it will skip the next instruction if whatever is in the register is equal to that byte. If the interpreter compares and they are equal, this increments the program counter by 2. So by 2 in this case means twice. So for 0x3, we're going to create var x and self.opcode and 0x0f00. That's where it is, and then you have to bit shift it right by 8 to grab that, to have this f be in this location at the end as the least significant byte. And then we're just going to do if self.registers at x is equal to self.opcode and 0x00ff. Then we're going to do self increment program counter, and then we're going to self increment program counter anyways. X1, 0x4. Surprisingly, it is literally the same thing, except not equal. So you can literally copy your code and then just say not equal. Boom. 0x5, what is this? So this is our first xy instruction, 5xy0. So it will skip the next instruction if vx is equal to vy. It's pretty much the same concept as here. Oops, let me 0x05 or 0x5, there we go. And you do that, except next thing you do is var y equals self.opcode and 0x00f0, and then we only bit shift by 4 to get the y. Then we just say if self.registers at x is equal to self.registers at y, we increment the program counter. Same exact thing. We're going to skip ahead a little bit. So 9xy0 is skip next instruction if not, so this is the exact same thing, once again. Very simple. So 0x9, and then you just add a not. Okay, going back, we're going to go to 6. 6xkk is set vx is equal to kk. So what this is going to be just loading a byte. And the way you do this is we're going to do 0x6. So once again, we gotta grab x. In this case, we gotta grab our byte, so kk. So var kk equal, well, we don't really need to. We can just say self registers at x is equal to, and then I have to use a truncate here just to be explicit about it, that we're going to shrink and cut off some bytes here. And self.opcode and 0x00ff. And that will basically ensure us that that kk here is going to be loaded into this register. The next thing is 0x7. This is our first mathematics instruction. So this one will be saying vx equals vx plus kk. So it's vx plus equal kk. So you're just doing an addition. So this one is pretty simple. The same concept as here, except it's just plus equals. Now, the issue is that in Zig, we have runtime safety, and that will throw an error if there is an overflow. So we have to set that to false here in whatever scopes we're going to be using unsafe instructions, because we want to acknowledge to the compiler that this is expected behavior, that we can have overflows. The next set is going to be quite a few. These are the ALU instructions, and they're the 8 set, 8xy0, 1, 2, 3, 4, 5, 6, 7, and E, because we couldn't go to 8. There's probably reasoning behind that. But 0x8. So if you notice, the last one is actually determining what the instruction is. So we're going to call that M as a, that's going to be mode. So xy, and then we're going to create the last one here, M equals self.opcode. And then it's just going to be and 0x000f. And that gets us our mode. So now, also, don't forget self-increment PC and self-increment PC as well. So we need to increment the program counter for all of these methods. And that will be true on this method as well. So the first couple of instructions here that we're going to do are going to be pretty simple. 0 is going to be in equals. So register X is equal to register Y. 1 is going to be an OR, so self registers X, OR equals self.registers to Y. And this OR is a bitwise OR, not a logical OR. Next thing is going to be 2 is going to be AND. And with OR and AND, you can pretty much create anything. And then 3 is going to be a XOR. So opposite. And you can use XOR to actually make a NOT as well. And 3 is going to be an XOR. So there, self.register at Y. Okay, that was the first 4. Those were pretty easy. However, now we have 4, 5, 6, 7, and E. What are these? It's going to be add, subtract, shift right, subtract N, which is going to be the opposite version of subtract, and I'll explain that a little bit more. Shift left, and then that's... So if you actually read these descriptions, it says set VF equals carry, set VF equals not borrow, set least significant bit of VX is 1, then VF is 1, and then this is VF not borrow again, and most significant bit is 1, then VF is 1. So this is where we're actually starting to modify that flag register as well. So you gotta keep that in mind. So for addition, we're going to have to do an at set runtime safety again, for the same reason. But then we're going to do sum. So for addition, we're going to create sum, and it's going to have a type promotion. So we're going to promote the X, and then we're going to do sum plus equals self.registers at Y. And we need that type promotion here, otherwise we can't catch overflows. And then we're going to take a look here, and then we're going to say that the flag register, so 0xf, is going to be set if sum is greater than 255. So we can do this inline if statement here. And then self.registers that X is equal to the truncated result of U8 with sum and 0x00ff. You can technically write it this way with the integer promotion for 0x7 as well, technically. So then 5 is going to be subtraction. This is going to be pretty much similar. So for subtraction, actually saying the flag is easier because you can just determine whether or not something is going to have a borrow or not based upon if self.registers at X is greater than self.register at Y. Because if it is, then there is going to have to be a borrow. So self-registers at X minus equals self-registers at Y. Let's go and skip ahead really quick for a very similar one, which is sub n, which is 8xy7. This is actually very similar to the previous sub, but the only difference is that if you read the equation here, vx equals vx minus vy for 8xy5, 8xy7 is literally the same thing, except vx equals vy minus vx. So we'll do that. Oops, that's 7, not 6. And you do literally the same thing. Flip the registers here to be y and x. And then this one will have to be self.registers at x equals self.registers at y minus self.registers at x. So we're almost done. We just need 6 and E. And pretty much it's very simple to do. The flag register self.registers at 0xf here will just be self.registers and 1. Because 1 is going to be the least significant. And then self.registers at x bit shift right equals 1. So this is equal to self.x equals self.x bit shift right 1. And whoops, I put that in 14. I meant to put that in 16. My bad. Or 6, sorry. And then the same thing happens here, except it's bit shift left one, and then this one actually needs to be a little bit more logic. If self.register is at x, and we're just going to use binary here. Actually, I think you can use 0x80. And then if that's not 0, then it's 1, otherwise it's 0. There you go. So that is everything through 0x9. We have a couple more instructions left. 0xa. So a here is going to be index is equal to nnn. So that one's pretty simple. It's basically loading an address. We're going to do an increment program counter. Self.index equals self.current opcode or opcode and 0x0fff. That one's pretty simple. Next one is 0xb. What does this one do? So bnnn is jump to a location at nnn plus the register 0. Program counter is set to nnn plus the value of v0. So for this one, we just say self.program counter equals self.opcode and 00fff, so that's nnn, plus we're gonna have to do a cast again to integer promote, self registers at 0. And that's that. Next one will be 0xc. And through 0xc here, we have, let's see, set a random byte and kk. This interpreter generates a random number from 0 to 255, which is then ANDed with the value k and stored in vx. This one is a little bit more involved, so let's set x equals set x here. And then we're going to create kk, which is self.opcode and 000ff. There you go. So you have x and kk. And then self.registers at x is equal to, this is going to be a bit. So we're going to do cstd.rand, so that's our random number. And then we're going to have to AND it against kk. And then we have to make sure that this gets truncated to a U8. Now that might still throw an error. I am not quite sure, but let me just round that up really quick. So we'll just do a zig build. Quick bug fix, self.registers. Here it should be self.registers at x. I apparently originally messed it up. And I was pretty sure about this, but I need to intercast this to be U32 so that we can perform an AND. And end of the switch cases need to have an else. Now here is a very complicated instruction. This is probably the most complicated actually, which is the draw instruction, and it's dxyn, where it displays an n byte sprite starting at memory location I at vxvy and sets the vf flag if there is a collision. This is a hard one to think of conceptually, so let's walk through it really slowly. We're going to go self registers at the flag, and we're just going to say that the flag is set to 0 to start with. We want to grab whatever is in register X and register Y real quick. So we want to grab, let's do XYN, or I'm going to call it XXYY and NN. So we'll do that, self. So then XX is equal to this. YY is going to just be equal to this, bit shift 4. And NN is going to be self.opcode and 0000f. So we have x, y, n. So we want to get the register x value, which is self.registers at xx. For register y, it's going to be self.registers at yy. So then we're going to go through two loops here. So the first one is going to be a while loop. So while y is less than our n value, y plus equals 1. So this will tell you how many lines there are on the sprite, and the sprite is always going to be 8 bits on the horizontal and n bits on the vertical. So we're going to get the current value, so this will be our we'll call it pixel, And we just need to grab the memory at self.index plus the current y value. And then we'll go var x, use size as 0. And we're going to say, while x is less than 8, then we're going to increment x. We're going to have constant value here. That's going to be our most significant bit. So let's call it MSB, I guess. So most significant bit. So this one is the big one. So if pixel and the most significant bit is shifted right by x, I have to cast it to U3 here for x. So now, once we have done that, we just now need to compare if it is set or not. So let's take an example here. If we read this from left to right, we have 0, 1, 0, 1, 0, 1, 0, 1. So if we read that, 0 here, this is what we're scanning for. Since it's 0 here, it doesn't matter. We're going to skip this pixel. But now when it's 1, we now realize that this pixel is being set, so we have to actually do the drawing logic. So we have to do the wraparound, so we're going to create this variable tx, and tx is equal to a register at x plus the x value. And then we have to make sure we do the remainder against the width. Width in this case is 64. We can do the same thing for ty equals register y plus y, but this is against the height, so it's 32. We can calculate an index from this, which will be tx plus ty times 64. This is how indexes work in flat arrays. You have to use one times the other. So we're going to do self-graphics at index, and then we're going to XOR it with 1. So if you actually look at what this does, it does say sprites are XORed onto the existing screen. If this causes pixels to be erased, the VF is set to 1. So if there was a pixel there, right, let's say, then graphics would be set to 1. So what's the result of 1 XOR 1? The result of 1 XOR 1 is 0. So we only need to check here for the flag if self.graphics at index is equal to 0, because then we'll do self.registers at 0xf is equal to 1. And normally this check wouldn't be fine if we didn't do this previous one. If we didn't do this previous one here, then this would actually set VF on any blank thing. But because it's specifically only when it gets set, now VF works correctly. And of course, at the end here, self.program_increment program counter. The next set of instructions are 0xe, so this is 0x90 and A1. And these are literally skip next instruction if the key is pressed or not pressed. So basically this will be used in an if statement, essentially. So we're going to grab the x value here, and it will have a kk value, which will be our mode, basically, in this case. So then if kk is equal to 0x9e, that's if it's pressed, and then else if kk equals 0xa1. And then all we do here is if self.keys at self.registers at x is 1, then we will self.increment program counter. Otherwise, if it's not equal to 1, then that's for the other case, and then we always have to increment the program counter anyways here. Next set of instructions is the 0xf, which is a bunch of miscellaneous instructions. It's pretty much the same format here where you have a mode selector. And we'll just use if-else if here. And at the bottom, of course, self.increment program counter. And let's go ahead and take a look at our instructions. So if we take a look, we have fx07, fx0a, fx15, 18, 1e, 29, 33, 55, and 65. These are all actually relatively simple. fx07 is load vx dt, so vx is equal to the delay timer. That one's incredibly simple to implement. So if the mode is 07, self.registers at x is self.delay timer. Otherwise, if the mode is 00a, we'll come back to this one. This one is going to be wait for a key press, store the value of the key in VX. We don't have key presses yet, so that's not exactly helpful to have. So we'll do an else if, and then we'll do kk equals 0x15. These ones are incredibly simple. So 15 and 18 are literally the same thing. They are set delay timer equals vx and set sound timer equals vx. So self dot delay timer equals self dot registers at x. And then the same thing happens for 0x18, except it's going to be sound timer. The next one is going to be 29. Actually, no, it's 1e, my bad. The next one is 1e, which adds an index plus vx. It's going to be self.index plus equals self.registers at x. The next one will be then if there is kk equals 0x29. 0x29 is the location of a sprite for digit vx. Value of I is set to the location for the hexadecimal sprite corresponding to the value of vx, which is 0 through f. So what you actually have to do here is you have to realize that this is actually looking for your CHIP-8 font set, which when we load it into memory was at 0. So we're going to start at 0, and then based upon what value it is going to be the memory address. There are 5 bytes here per each image, so it's going to be times 5. So to do that, we just got to do self dot index equals self dot registers at x times 0x5. You might want to do safety check here, where you check self dot registers at x is less than, or yeah, is less than 16. There are plenty of other places you can put safety checks as well. So 0x33, this stores the BCD representation of Vx in memory locations I plus 1, I plus 2. Basically what you're doing here is you are literally taking the individual numbers. So if I have a number 137, I would store the hundreds value first, so 1, and then I plus 1 is going to be the second value, which is 3, and the next value will be 7. So it's basically just performing what are the digits of a number. And this is actually incredibly easy to implement. You just use self.index equals self.registers at x. First one is divide by 100. Second one is going to be divided by 10. But now, what happens if it's 130? It's going to be 13. You want it to be 3, so you have to do a modulus, so a remainder. And then index plus 2. And then this one is going to be literally mod 10. Next one is 0x55. 55 and 65 are basically the same thing, so hold on, let me just copy that. 65 and 55, there we go. So for 0x55, what does it do? Stores registers v0 through vx in memory starting at location I. So what this does is that we're basically doing a for loop here, 0, and then we're going to do while I is less than or equal to x. We're going to do I plus equals 1. And then what you do in this loop is just self.registers at I is equal to self.memory at, or sorry, I did that the reverse way. Self.memory at self.index plus I is equal to self.registers at I. This one is going to be dumping all of the registers into memory. Now the opposite of this is going to be this one, where we do self.registers at I is equal to the is equal to the memory. So this one loads it, and that's what this one does. And then last one here, 0x0a. This one's complicated because basically it's just going to wait. It's going to waste cycles every time it does this. So we have to check if a key is pressed. So by default that's false. Then we can go through the entire key array. So let's go usize equals 0. I mean, technically I could just do for self.keys and then check the value v. And then so if self.keys at value v is equal to or is non-zero, then the key press has to be true. We have to do a break, and then we also have to check self.registers at x equals which key was pressed. and I need an index here. There we go. And like that, we have a method there. And then what we have to do to burn the cycle if it doesn't, if it's not pressed, is you do if not key press, and then you just do a return. And that will just keep rerunning the same instruction. It will not get to the self.increment PC here. So you can keep going over and over. And this line is basically just saying that if the key is pressed, set the register equal to whatever key was pressed. However, now if you go and run it, nothing actually happens. And why does nothing happen? Well, nothing here happens specifically because, well, we didn't give it any input. There's nothing that's running. It's running 000, which is just being ignored until eventually it will just run out of memory space and probably crash. So, should probably close it. Well, okay. Now what do we do? So, we have everything here except one important thing, which is loading a ROM. Now, loading a ROM is pretty simple. You just want to grab, so in this case, if we're going to run it from the command line, we're just going to grab a command line argument. So we can go ahead and get a command line argument. You want to get the file name. So in Zig, I'm going to create an iterator for arguments. Try process.args with allocator. And then we're just going to use the allocator we already have. And then we're going to say, we're going to skip the first one, because the first argument is always going to be the name of your program, or the path to your program, which is helpful when you want to get a current working directory, but not so helpful when you're trying to get the actual arguments. So then we're going to create a file name, which will just be the next value. And if this gives us an error, we're just going to do debug print dot debug print, and then we're just going to say no ROM given, and yell at the user because they're stupid. And there we go. So then we got to load a ROM. So let's create a function to do that. We'll do public function load ROM, and it creates what does it need? From what I think here, we'll just need the file name. So to do this, we're going to create a file with whatever programming language. So file system, current working directory, open a file at the file name. We're not going to give it any flags. Then close it at the end. So input file close at the end. And then we're going to we need to get the size. So in certain languages or certain architectures, you want to seek to the end. So we're going to do input file get end position, and that'll give us the relative size of the ROM. And then we'll create a reader for it. So we'll create a reader, var reader, so input file reader. And with however method you've gotten this, we're just going to basically be doing a loop over the size. So while I is less than size, I plus equal 1. And you're just going to say your CPU.memory at I plus, you have to do a plus offset to the initial 512 bytes, because that's where our program counter is. And we're going to do try reader.read byte. And you can do this however you want in whatever programming language. And that's how you load a ROM. Then we're just going to do try load ROM. So there's this very nice repository on GitHub that you can clone into yours. It's called CHIP-8 ROMs, and we'll go ahead and clone that over. So one thing that I like to do when I have a bug is debug print, and we're just going to print out whatever the cycle is. So whatever instruction we're currently executing, so self.opcode. To build a texture with STL, it's pretty simple. You need a array which you can access. So U32 is null, and we'll set the pitch as a cint. Pitch as a cint equal to 0. First thing you gotta do is you gotta lock the texture. So STL lock texture, and it'll be texture null The pixels will be, we're going to do a pointer cast here. We have to do a pointer cast. To pointer C question mark pointer any opaque. That looks terrible, but it's what's necessary. And then submit the bytes as well, and then the pitch. So then we have to do and pitch. We don't actually care about the pitch, but it just needs to exist. STL.stl unlock texture will also be done here. And it needs texture again. So now, what are we gonna do? Pretty much we can do a for self.graphics or not self, CPU.graphics. For CPU.graphics, we're going to get G and we're going to get an index. And then bytes at the index is going to be equal to if CPU.graphics at the index is equal to 1. If it is, then we fill it with the value for white, which is all Fs. Otherwise, it is going to be black with alpha. And now, there we go. We get an OK on everything, meaning all of our tests have passed here. However, let's run it through the other test method as well. This test is a little bit more thorough, and it tells us that number 16 fails. Let's check what that means. FX07 fails because the delay timer is not implemented. That is correct. I did forget to do that. So for the delay timer, we just go to the end here of the function. Yes, I believe so. And then we say if delay timer, or if self.delay timer greater than 0, self.delay timer minus equals 0, or minus equals 1, sorry. Same thing happens for the sound timer. Although for the sound timer, you should technically play a sound here. Although, we can ignore that for now. And there we go, everything else is okay. So you can run through a bunch of these test programs now. Let's do the CHIP-8 picture. And it displays this nice CHIP-8 here on the screen. Another one we can do is going to be the BMP viewer. That one I showed at the beginning. Give it a second, and it draws the hello from the start. You can also go through some of the other ones. Maybe the fishy should draw a fish. It does. Minimal game here. Should have this little flashing guy. Framed MK1 draws this like frame thing around it. And then what it should do is it should start tracing a really random path. And this path can go wherever it wants to. So you'll see this thing randomly decide to go and move around. That's a test of your random number generator. Another one you can do is square root. Square root test here. Square root of 144 takes its time to load. But the result here, square root 144, should be 12. Of course, now we have games like Pong. But we seem to have a problem here. The issue that we're going to have is going to be that we can't move because we haven't implemented keys yet. Now, we have implemented everything except keys, and pretty much we just gotta put the keys into SDL. So I'm going to create a map of scan codes corresponding to each and every single key press. So this is the scan code map. So this might not necessarily be clear, but 0, where is 0? If you remember the image of the keypad, give me one moment. You want to correspond the number value with the key value. So index 0 of the array is where the 0 key is. Index 1 of the array is where the 1 key is. So on and so forth. And we're pretty much using 1, 2, 3, 4, QWE, R, ASDF, ZX, YC as the ones, but we're reordering it in that fashion. And what this allows us to do is write some very simple code here where we do SDL key down. Var, we'll just do a simple loop here. uSize is 0, while I is less than 16, I plus equals 1. If E, so the event, key symbol scan code is equal to the key map at I. Then we'll do our CPU dot keys at I is 1. Now we can do the exact same thing for STL key up, except we're just gonna set it to 0. Now if you run Pong, Q I believe brings you down, and 1 brings you upwards. And then the dot will come back to us. And we can block it. And boom. It's now going back up. Now, there is a bit of stutter to this, and there's multiple solutions to fix the stuttering, but let's go ahead and remove the print spam, and congratulations, you actually have your first emulator. Now, things that you can do to continue with this is, one, you would probably want to get these delay timers to be, you would probably want to remove the delay timers from being within the cycle. You'd want the delay timers to be separate, maybe even to the point where you create just a separate thread that's dedicated to making sure those timers are being incremented and decremented correctly. Decremented correctly. The other thing that you can do is, of course, adding sound. So whenever this is true, inside here you would add sound. So you create a full if statement. And then another thing you can go experiment with is changing the colors. You can change the color of the background and the foreground, stuff like that. And then, of course, there's more to go on with the CHIP-8 emulator. You can start mimicking Super Chip, so Super Chip 48 or whatever it's called. It adds another 10 instructions, and then you also have some games that will have, for example, some games do indeed have this thing where they can do 64 by 64 mode, or 64 by, I think it is 64 by 64, where it can have extra pixels, and you can go ahead and try and figure that out. These are just some ideas of what you can do to go ahead and get better. You can go ahead and just essentially create better results here. It could be a very good practice if you want to get into emulators, and I hope to continue this series, maybe starting with a more advanced project like an NES emulator or something later on. Congratulations on your first step, and I'd love to see your progress in the comments below, and have a great day.